In this video, we're going to introduce the idea of spectroscopy. What is spectroscopy and why is it useful to chemists? For the most part, what's going to help us today is to really use spectroscopy to understand infrared spectroscopy, which is important to organic chemists because it helps us identify functional groups. A functional group is something in an organic molecule that undergoes a characteristic chemical reaction. And some of the functional groups that we're going to become familiar with and be able to identify by infrared spectroscopy are hydroxyl groups that are found in alcohols. We're going to be able to identify NH bonds in amines. We're going to be able to identify carbon-oxygen double bonds. These two, this OH group and this carbon-oxygen bond, double bond, are the ones that are going to be the most important and the most useful in infrared spectroscopy. So before we go into infrared spectroscopy, I want to sort of talk about what is spectroscopy, because it turns out that we're all familiar with spectroscopy. So if you think about why is a leaf green, what you want to realize is that spectroscopy happens all the time. Any kind of spectroscopy involves a source, which in this case for a leaf is that the source is the sun. So the source is the thing that's emitting light. And the thing that you need for infrared spectroscopy or for visible spectroscopy, which is how your eye works, is a source that emits a lot of different wavelengths of light. So the whole spectrum of light from red all the way through to purple. Then what you have is you have your leaf, and the light is shining through the leaf. Some of that light is absorbed by the leaf, and some of that light is transmitted. So I'm going to depict that with fewer lines coming out. So some of these wavelengths of light were absorbed by the leaf. Some of them were transmitted. So these are the wavelengths here that are transmitted. And then those wavelengths make it to your eye, and what you see in your brain is green, because these wavelengths here are green. So same thing happens in an instrument in the laboratory, except now what you have is you still have a light source. It's not the sun in this case, it's some kind of other light source, and then you're going to have a sample. In the previous case it was a leaf, but in infrared spectroscopy is going to be a chemical that you want to analyze, and here you're going to have your detector, which measures the wavelengths of light. So there's lots of different ways that we can graph this, but the way that's going to be most useful to us is kind of shown here at the bottom, where on the y-axis we have percent transmittance, and then on the x-axis we have wavelength. So notice that if you have, and this is actually the visible spectrum of a leaf, or chlorophyll actually. So notice that here not very much of the blue or purple light is transmitted, because right here would be 100% transmittance. So that means that most of the blue and purple light is absorbed, some red light is absorbed, but you'll notice here that 100% of the green light is transmitted to the detector, which is a reason why a leaf is green. So a leaf is green because it doesn't absorb green light. And we're going to use this analogy to understand how infrared spectroscopy and other forms of spectroscopy work. So remember from general chemistry that there's lots of different energies associated with different kinds of light. So what we see every day is this spot right here, the visible spectrum. We're going to move over here for the duration of this video to talk about infrared light. So if you go down here to this sort of table, what you'll notice is that visible light is a very narrow band of the electromagnetic spectrum, and each different kind of light causes different things to happen in molecules. So for example, X-rays cause electrons to be emitted from atoms or molecules, whereas infrared light causes atoms to vibrate. So what you're going to have is a bond between two atoms, and that bond is going to start vibrating. So when you absorb infrared light, it causes bonds to vibrate, and different bonds have different energies, and so those different energies are going to cause different wavelengths of light to be absorbed, and we'll go into that in a little bit more detail. So the way you want to understand infrared spectroscopy is to imagine a bond between atom A and atom B as a spring. And when a certain wavelength of light shines on that spring, then what's going to happen is that spring is going to start vibrating. And the energy associated with that light is going to correspond to the energy that it's going to take to make that spring vibrate. So different wavelengths of infrared light are going to cause those bonds to vibrate. And so what we can see is different kinds of bonds based on the different energies of infrared light that are absorbed. So let's think about the consequence of this, right? What are we going to be able to identify? What infrared allows us to do is identify types of bonds. So what it tells us is that there's certain kind of bonds that are present in a molecule. For example, if you look at these two infrared spectra, you'll notice this very characteristic peak that's present in both. And this tells us that there's an OH group present. So this peak right here tells us, yes, there's an OH group present, but it doesn't tell us what the structure of the molecule is. It just tells us that there is an OH group present. So IR is usually just one piece of the puzzle. It tells you what functional groups are in the molecule, but it doesn't tell you the overall structure of the molecule. Stated another way, what we could say is infrared spectroscopy would not allow us to differentiate between these two molecules. So here we have 2-propanol, and here we have 2-butanol, and notice that their infrared spectra are very similar, and we wouldn't be able to tell them apart. We would just know there is an alcohol present in the molecule. So to summarize, we're going to use infrared spectroscopy to identify types of functional groups. Okay, so there's other kinds of things that infrared light can do to molecules. So what we're mostly going to be focusing on is stretching, but what can happen is atoms can move toward each other, which is called bending or scissoring, or they can move in the same direction, which can be called bending or twisting. So there's all kinds of other transitions that are going to happen. These are going to happen at lower energies. It takes less energy to bend a bond than it does to vibrate a bond. These are higher energies. And so this is the region of the infrared spectrum that we're going to focus on. And like I said, different bonds have different strengths and vibrate at different frequencies. So you can see that a CH bond vibrates in a different spot than a CO bond, which vibrates in a different spot than a carbon-chlorine bond. And the way that I want you to sort of think about this is to imagine that spring analogy that we had on the opposite page. So if we had the same spring, which is the same bond, but let's say we have a really big bond here, and it's attached to a really small atom. If we pull this atom back and let go, it's going to vibrate really fast because this atom right here is not really going to be moving at all. So that's going to be a fast vibration, which is high energy. So to summarize, a small atom attached to a big atom is going to be a fast vibration, and we're going to see that over here at 3,000 wave numbers. Whereas, let's imagine that we had two big atoms attached to each other. Well, now what's going to happen is they're going to vibrate really slowly. So that's sort of this situation over here. So when you're looking at comparing different kinds of single bonds, the thing you want to think about is the size of the atoms. Smaller atoms, or at least one of them being smaller, is going to cause a faster vibration. So then the other thing you can think about in IR spectroscopy is the strength of the spring that's connecting those atoms, and that has to do with the type of bond. So a triple bond is going to be a stronger spring than a double bond, which is going to be a stronger spring than a single bond. So since the spring is stronger, this bond is going to vibrate faster, this bond a little bit slower, this bond really slow. So the two trends that you want to use to help you understand infrared spectroscopy are size of atom and strength of bond, or in other words, is it a triple bond or a double bond or a single bond? So the way we describe this in infrared spectroscopy is that we have a diagnostic region, which allows us to see different kinds of bonds, and then we have a spot where everything kind of overlaps. So we're going to ignore this part of the infrared spectrum. This is called the fingerprint region, and that is not going to be of any use to us. So anything below 1500 wave numbers is going to be useless. So what can we see in the infrared spectrum? We can see double bonds, we can see triple bonds, and we can see bonds to hydrogen, namely OH bonds and NH bonds, because every organic molecule is going to have a CH bond, so that's going to be kind of useless to us. The one exception to that rule is that certain flavors of CH bonds will differentiate themselves. For example, if you have a CH bond bonded to a sp hybridized carbon, that's going to be shifted far over to the left compared to where you usually see your sp3 CH bonds. Your sp2 CH bond is going to be shifted over a little bit less. And notice that all your sp3 CH bonds are always going to be clustered here between about 2800 and 3000. So this is going to be present in virtually every single infrared spectrum that we go over in this video and that you're going to see in the lab. All right, so these are the functional groups that I want you to get familiar with that we're going to be able to identify by infrared spectroscopy. Many of these we've already talked about in class. Alkene has a carbon-carbon double bond. Alkyne, carbon-carbon triple bond. Alcohol contains an OH group. Then there's many functional groups that contain carbon-oxygen double bonds. A carboxylic acid is a carbon-oxygen double bond that's also bonded to an OH group. An ester is a carbon-oxygen double bond that's bonded to an OR group. So there's no hydrogen here, there's a carbon. An aldehyde is a carbon-oxygen double bond that's bonded to a hydrogen. A ketone is like an ester, but there's a carbon here bonded to the carbon-oxygen double bond. Then we're going to have a primary amine, which is this NH2, which means that the nitrogen is only bonded to one carbon, and a secondary amine, which has a single NH bond and two nitrogen carbon bonds. So let's go over some examples of these. The first one I have is 1-heptene. So notice the kinds of things that we're going to be able to see in the infrared spectrum are this carbon-carbon double bond and these unique CH bonds that are on sp2 hybridized carbon. So first let me point out, this is where you always see sp3 hybridized CH bonds. That's going to be in every single infrared spectrum, so we can ignore that. We can also ignore the entire fingerprint region. That's useless. So what peaks are left? Well, we have this peak that I've labeled at 1625. That's going to be our carbon-carbon double bond. And we know that because that is a characteristic region where we see double bonds. And then here, shifted slightly to the left of the sp3 hybridized CH bonds is this CH bond, which is on an sp2 hybridized carbon. So that's how you identify an alkene. For an alkyne, it's similar, but notice now we have this peak. We're going to ignore the fingerprint region. We have this peak, which is our carbon-carbon triple bond. That's shifted over to the left compared to where we saw the carbon-carbon double bond. So that's very characteristic, and there's nothing else that's really going to show up in that region. And then we have our CH bond that's on the end of our alkyne, which is shifted way over. That's our sp-CH bond, shifted way over from where we see our sp3 CH bond. So let's say this molecule was this, for example. All of these CH bonds, this one and this one and this one and this one are all going to show up here. This single CH bond is going to show up here, and then our carbon-carbon triple bond is going to show up here. A lot of infrared spectroscopy is process of elimination. So there's no double bonds, there's no OHs, so that allows us to eliminate or exclude a lot of functional groups that I listed at the, before I started going over these spectra. So how do we know how to identify an alcohol? Well, there's a very characteristic way, which is this peak, which looks like a tongue. So sometimes we call this the OH tongue. This tells us there's an OH present. It's a very broad It's a very broad peak, and it's very clear that there's an OH group present. There's no other infrared peak that looks like this. We still have our sp3 CH bonds. Let's say we have one propanol. We'll notice that there's all kinds of sp3 hybridized CH bonds here, which are all overlapping here in this peak. We're going to ignore all of this crap. Note there's no carbon-oxygen double bond, or there's no double bonds or triple bonds to speak of in this region. So that allows us to figure out that it's not a ketone, it's not an ester, it's not a carboxylic acid, it's none of those functional groups that contain carbon-oxygen double bonds. It's not an alkene, it's not an alkyne, it doesn't have any double or triple bonds in its structure. Carboxylic acids are easy to identify too, because unlike the tongue that we saw in the previous slide, this kind of looks like a beard, like a Santa Claus beard. It's a much wavier, broader OH peak, and it also comes along with a very characteristic carbon-oxygen double bond. So the combination of a carbon-oxygen double bond and an OH peak tells us definitively we have a carboxylic acid present, in this case, acetic acid. So we see a sharp carbon-oxygen double bond peak and a very broad and jagged OH stretch, which is often described as a beard, which is the characteristic telltale sign of a carboxylic acid. An ester is going to contain a carbon-oxygen double bond, which is a sharp peak between about 1710 and 1760. No OH peak. We still have our sp3 CH bonds. We're going to ignore all this crap. So really, there's only a carbon-oxygen double bond. This could be an ester. An ester, remember, looks like this. It's hard to differentiate esters and ketones, so you're going to need additional information to know the difference between a ketone, which has a carbon on the end, or an ester, which has an oxygen bonded to the carbon-oxygen double bond. Here we have heptanal. Remember, an aldehyde has a hydrogen on the end bonded to the carbon-oxygen double bond. Here we see our characteristic sharp carbon-oxygen double bond peak, but the CH bond of an aldehyde is shifted over to the right compared to the rest of the sp3 CH bonds. So that tells us there's an aldehyde present. This peak right here does. There's no OH peak, so we can exclude alcohol as a possibility. Like I said, ketones and esters look very similar. Really, the only thing that is going to stick out to us here is the presence of this carbon-oxygen double bond peak. A primary amine, remember the bonds to hydrogen show up in this region. It's not broad, it's sharper, but it is shifted over to the left compared to where we see our sp3 CH bonds. The fact that we have two peaks here tells us that we have two NH bonds. Aniline looks like this. It's a primary amine, and there's two NH bonds. This shows up as vampire fangs. And that's sort of the characteristic, let me erase this so you can see that. That's the characteristic way to identify a primary amine is with the vampire fangs. Whereas if you had secondary amine like methylaniline, now you only have one NH bond. So you only have one sharp peak here from the single NH. Okay, so just to give you a little bit of practice on this, I'm going to give you a minute. You can also pause the video if you'd like to have more time to figure out what functional group you think is present. So the kinds of questions that you're going to be asked is to differentiate between different functional groups. So what you want to do is try to figure out what characteristic things do I see in the infrared spectrum that can allow me to figure out what functional group is present. Okay, so the kind of things that you want to look at here is that you have a very broad beard peak right here. You have a very characteristic sharp carbon-oxygen double bond. That tells us that there's a carboxylic acid. It's not an ester because this beard wouldn't be present if it was an ester. It's not a primary amine because then we would see fangs over here in this part of the spectrum. It's not an alkene because we also wouldn't see the beard in that case. So a lot of times you're going to use sort of process of elimination to figure out what the correct answer is. We have a carboxylic acid. Next one we're going to look at is this guy. So I'll give you a second to think about what you think the answer is. And again, if you want to pause it and try to come up with your answer, you're more than welcome to do that. Again, we're going to use process of elimination. Here's an alcohol. We would see a broad OH tongue in this region of the spectrum if that was present. Since it is not, we know that it is not the alcohol. Alkenes usually have a CH peak that's shifted over a little bit to the left, which we don't see, so that is not correct. NH2 would be vampire fangs here, which are not present. However, there is a very clear carbon-oxygen double bond peak here at 1711, which tells us that we have a ketone or an ester present. But since the ketone is the only possibility on the list, then that must be the correct answer. Okay, so to summarize, I've been going on for a while here. To summarize, here are the things that you want to look for in infrared spectroscopy. You want to look for a very characteristic dip, which indicates that the molecule is absorbing infrared energy and identifies a specific kind of bond that's present. So these are the characteristic peaks that I want you to be able to identify. The OH or NH peak is going to be the furthest to the left. NH tends to be a little bit sharper. OH tends to be more broad like a tongue. Then you have the alkyne CH peak, the alkene CH peak, and then the sp3 CH peak, which is present in virtually all organic molecules. Next, so this is all the area of the infrared spectrum where you see bonds to hydrogen. Then we're going to see double bonds between two different atoms. And the ones that are going to be really helpful for us are carbon-carbon triple bonds, carbon-nitrogen triple bonds, carbon-oxygen double bonds, carbon-carbon double bonds. Notice that carbon-carbon double bonds are shifted to the right compared to carbon-oxygen double bonds, which is a nice way to be able to tell those apart. So what I'm going to want you to be able to do in lab or in the class is be able to match infrared spectra with compounds like we did on the last two slides, and use process of elimination to determine which IR spectrum matches, which we also did on the last two slides.